Hello everyone, today I'll be going through all of the challenge questions in Edexcel's Pure Year 1 textbook, Chapter 7. Okay, our first question is from exercise 7c, and it says f of x equals 2x to the power of 4 minus 5x cubed minus 42x squared minus 9x plus 54. And part A says show that f of 1 equals 0 and f of minus 3 also equals 0. So first of all, f of 1 is equal to 2 minus 5 minus 42 minus 9 plus 54, and if you pop that in your calculator you should get 0. And now for f of minus 3, we'll have 2 times 81 minus 5 times minus 27 minus 42 times 9 minus 9 times minus 3 and plus 54, and if you pop that into your calculator you should also get 0. Now part B says hence solve f of x equals 0. So by the factor theorem we know that x minus 1 and x plus 3 are factors of f of x. So therefore we know that x minus 1, x plus 3, which is equal to x squared plus 2x minus 3, has to be a factor of f of x too. Okay, now using polynomial long division. So we have x squared plus 2x minus 3 on the outside, and on the inside we have 2x to the power of 4 minus 5x cubed minus 42x squared minus 9x plus 54. Okay, so our first term on top is going to be 2x squared, so we get our 2x to the power of 4 here. We have plus 4x cubed and minus 6x squared. So taking this away, we get minus 9x cubed and minus 36x squared. And we carry the minus 9x over. So our next term is going to be minus 9x. So we get our minus 9x cubed here, minus 18x here, and plus 27x at the end. Now taking these terms away, we will have minus 18x squared here, and we have minus 36x here, and we add the plus 54 in the end. And our last term is going to be minus 18, and that will give us our minus 18x squared. Minus 36x and plus 54, and taking those away we get 0. So that is our division complete. And so our other factor is 2x squared minus 9x minus 18. And now we can see if we can factorize this as well. So we're looking for two numbers that multiply to minus 36 and two numbers which add to minus 9. And here those two numbers will be minus 12 and 3. So we get 2x squared minus 12x plus 3x minus 18. And we can factorize both parts. So here we get 2x into x minus 6. On the other side we get 3 into x minus 6. And so our factorized expression is 2x plus 3 x minus 6. So we now have that f of x is equal to x minus 1, x plus 3, 2x plus 3, and x minus 6. So to solve f of x equals 0, we have the solutions x equals 1, x equals minus 3, x equals minus 3 halves, and x equals 6. And those are our four solutions. Okay, our next question is from exercise 7d. Question 1. Prove that A 7, 8, B minus 1, 8, C 6, 1, and D 0, 9 are points on the same circle. So to do this question, we can use the fact that we can find the center of a circle by finding the intersection of two perpendicular bisectors of two chords of the circle. So I'll show you what that looks like. So for example, if we have these 3 points on the circle, we can take this chord here and this chord here, and if we take the perpendicular bisectors of both of these lines, their intersection will be the center of the circle. So in this question, we can find the circle that goes through these 3 points, A, B, and C, and then we can show that D also lies on the same circle. So we can use the fact that these 3 points are on the circle to say that AB and AC are chords of the circle, and therefore we can find the 2 perpendicular bisectors to these chords, and their intersection will tell us where the center is. So let's try first to find the perpendicular bisector of A and B. So on a graph, A and B would look something like this. Because these 2 points have the same y coordinate, finding the perpendicular bisector here is quite simple. You're looking for the vertical line that goes straight through the middle of the line segment AB. So here is the point M, which will be 7 minus 1 over 2, so that's 3, 8. So this line is line x equals 3. Now, the perpendicular bisector for AC, so we have C, 6, 1, and we have A, 7, 8. Here, we can find the midpoint. So the midpoint here is going to be 6 plus 7 over 2, so that's 13 halves, and 1 plus 8 over 2, so that's 9 halves. Now we need to find the gradient of AC, which is 8 minus 1 over 7 minus 6, which is 7 over 1, which equals 7. So the gradient of the perpendicular bisector here is equal to minus 1 over 7. So using the equation of a straight line, we get y minus y1 is equal to the gradient times x minus x1. Okay, now finding the intersection point of these 2 lines here will give us the center of the circle. So plugging x equals 3 into here, we get y equals minus 1/7, 3 minus 13 halves, plus 9 halves. So we get that is equal to minus 7 times 6 halves minus 13 halves, so that's minus 7 halves. So minus the 7 of minus 7 halves is going to be a half, plus 9 halves gives us 5. So we know that the center of the circle has the coordinates 3, 5. So here we can take any point. I'm going to go for C, 6, 1. So we have C, 6, 1 here. And we'll have 3, 5 over here. That's the center. So the radius is this length here. So r equals the square root of 6 minus 3 squared plus 1 minus 5 squared. So that's 3 squared plus 4 squared, which is 25. So the square root of 25 is 5. So we know the radius has length 5. And so the equation of the circle is x minus 3 squared plus y minus 5 squared using the center is equal to r squared, which is 25. So all we need to do now is show that the point D09 lies on this circle. So trying the point 09 here, we get 0 minus 3 squared, so 3 squared, plus 9 minus 5 squared, so 4 squared, is equal to 25. And so the point D lies on the circle, and so all 4 points lie on the same circle. Okay, for question 2, prove that any odd prime number can be written as a difference of 2 squares. So we can look at some examples. So the first odd prime number is 3, and we know that 3 is equal to 2 squared minus 1 squared. Our next odd prime number is 5, which is equal to 3 squared minus 2 squared, 7, which is equal to 4 squared minus 3 squared, 11, which is equal to 6 squared minus 5 squared, and we can start to see a pattern emerging here, and that is that the odd prime is equal to some number squared minus that number minus 1 squared. This is equal to a squared minus a squared minus 2a plus 1, or 2a minus 1. And you'll see that this is the general form of an odd number. So it turns out we can write any odd number as the difference of two squares by using this form here. So for example, if you wanted to find the difference of two squares that gives 17, then we know that 2a minus 1 equals 17, so 2a equals 18 and a equals 9. So to get 17, all we have to do is 9 squared minus 8 squared, and we can check that equals 17, 81 minus 64, which does indeed equal 17. So we have shown that any odd number can be written as a difference of two squares, and therefore every odd prime number can be written as a difference of two squares. Okay, and finally our mixed exercise 7 questions. Question 1. The diagram shows two squares in a circle. Given that pi is defined as the circumference of the circle diameter 1, prove that 2 root 2 is less than pi is less than 4. So the first thing we can note from this diagram is that the perimeter of the inner square is going to be less than the perimeter of the circle, or the circumference of the circle, which is going to be less than the perimeter of the outside, the outer square. Okay, we know that the diameter of the circle is 1, so we can draw in the diagonal of the inner square as 1. So if we look at this right angled triangle here, you know that these two angles must be 45 degrees. And so we have a right angled triangle with hypotenuse 1, which is isosceles. If we call these side lengths x, we know it must be equal. And now using Pythagoras, we get 1 squared equals x squared plus x squared. So 2x squared equals 1, so we get x squared must equal a half, and therefore x equals 1 over root 2, as we know x must be greater than 0. So therefore the perimeter of the inner square is equal to 4 lots of x, 4 lots of 1 over root 2, which is equal to 4 over root 2. Multiplying top and bottom by root 2, we get 4 root 2 over 2, which is just 2 root 2. So the perimeter of the inner square is 2 root 2. Okay, right. Now we need to find the perimeter of the outer square. We know the outer square has side length 1 from the diagram. The circle has diameter 1, so the side length of the outer square must be 1. So our perimeter of the outer square is just 4 times 1, which is 4. And we know that the perimeter of the circle, the circumference of the circle, is pi, as we're given in the question. So we get the inequality 2 root 2 is less than pi, which is less than 4, as required. Okay, for part B, by similarly constructing regular hexagons inside and outside a circle, prove that 3 is less than pi is less than 2 root 3. So I will try my best to draw what we've got going on here. So we have a circle, and we've got a hexagon inside the circle, and we've got one outside as well. So if we just focus on the hexagon on the inside, first of all, if we look at the center of the circle and draw out 2 radii, like so. So these radii will have a length of a half, as the diameter of the circle is 1. And we also know that this triangle will be 1/6 of the hexagon, as we have 6 different segments like this. So we know that this angle here has to be 60 degrees. And because we have an isosceles triangle with one angle 60 degrees, we know that this must be an equilateral triangle, as all angles must then be 60 degrees, and so all side lengths are 1/2. And so that means the perimeter of the inner hexagon is equal to 6 times 1/2, which is equal to 3. And now if we focus on the outer hexagon, I'll draw that in red here. So that will look something like this. Okay, not great. Let me try that side again. There we go, slightly better. Okay, now we can do the same thing here. If we look at, say, this red triangle here, if we draw the perpendicular from the center down to the midpoint of this side of the hexagon, we'll have a 90-degree angle here and a 30-degree angle up here, as this is half of the bottom segment of the hexagon, like so. So we have a 30-degree angle up top there, and we know that this side here is the radius of length a half. So we know that this side length here, if we do tan of 30, we get the opposite side over 1/2. So we know that the opposite side is equal to a half tan 30, which is equal to a half times 1 over root 3, so 1 over 2 root 3. And we know that we've got that is half of the side length of the outer hexagon. So that means the full length of the outer hexagon is 1 over root 3. And we need 6 lots of that. So we get 6 over root 3, multiply top and bottom by root 3, we get 6 root 3 over 3, which is 2 root 3. And therefore we have shown that 3 must be less than pi, is less than 2 square root 3. The same reasoning as the squares, that the perimeter of the inner hexagon must be less than the perimeter of the circle, which must be less than the perimeter of the outer hexagon. And finally, question 2, prove that if f of x equals ax cubed plus bx squared plus cx plus d, and f of p equals 0, then x minus p is a factor of f of x. Okay, here we can do long division on f of x. So we have x minus p on the outside, and on the inside ax cubed plus bx squared plus cx plus d. Now, our first term on the top will be ax squared, to give us our ax cubed here, and minus px squared. Now, taking that away, we get b plus px squared, and taking the cx down. Our next term will be b plus px, so we get our b plus px squared here, and then our minus b plus px. Taking this away, we now have c plus b plus x, and then adding the plus d on the end, our final term will be plus c plus b plus p. So there should be brackets around it. Okay, and finally multiplying that through, we have c plus b plus p, x minus p, c plus b plus p. And taking this away, we get our remainder is d plus p, c plus p, b plus p, which is equal to d plus cp plus bp squared plus p cubed. Okay, now we can see what f of p equals. So we have a p cubed plus b p squared plus cp plus d, and we know that that must be equal to 0 from here. And this here, you can notice that this expression we've got here is the exact same as the remainder. So we know that the remainder must equal 0 if f of p equals 0. So therefore, if f of p equals 0, then we know that x minus p leaves a remainder of 0 when f of x is divided by it. So x minus p is a factor of f of x as required. And that is the end of Edexcel's Pure Year 1 Chapter Challenge question walkthrough. I hope you enjoyed, Hope to see you for chapter 8.